And gentlemen, myself Hafiz Ahmed, lecturer, Department of Mechatronics Engineering, Kuwait. Along with me, we have Muhammad Mahfuzur Rayhan and Ahnaf Tanjid as a moderator to provide any sorts of technical support to this session. Today, we are in the first day of International Conference on Automation, Control and Mechatronics for Industry 4.0. Current time is 10 a.m. Bangladesh Standard Time. I would like to welcome all of you in the keynote session 1 of ACMI 2021. On this special occasion, we feel honored to have Professor Dr. Zhiyong Chen, University of Newcastle, Australia, as a keynote speaker. ACMI 2021 has got a new dimension to have such a resourceful person like him. So, dear audience, this is time to welcome our honorable keynote speaker, Professor Dr. Zhiyong Chen, with big round applause. Thank you for your appreciation. It's our immense pleasure to have Professor Dr. Mohammad Selim Hossain from Russia University of Engineering and Technology as chair and Dr. Muhammad Humayun Fuad Rahman from UNSW Australia as co-chair of this keynote session. After the end of the keynote session, there will be a question and answering session. All the audience are requested to write questions, if any, in the chat box. Audience can also raise hand in the Zoom after the end of the presentation. Now, I would like to request our honorable chair and co-chair to take the floor and introduce our honorable keynote speaker to the audience. Thank you.
Thank you. Honorable teacher, distinguished guests, researcher, ladies and gentlemen, very good morning and greetings to you. Assalamu alaikum wa rahmatullah. I am Dr. M.D. Selim Hossain, the Professor, Department of Electrical and Electronic Engineering,
Recording in progress.
University of Engineering and Technology. I did PhD from Australia, UNSW. My role as a session chair and my colleague, there is a session co-chair, Dr. Humayun Fuad Rahman, Research Associate from UNSW Australia. Before starting the session, I would like to introduce Professor Zhiyong Chen, University of Newcastle, Australia. Dear audience, we will listen valuable speech about the secure network control of large-scale cyber physical systems using cryptographic techniques. You know that Dr. Zhiyong Chen, he is the senior member of IEEE. He received the Bachelor of Engineering degree from the University of Science and Technology, China in 2000. And he also received MPhil and PhD degrees from the Chinese University of Hong Kong in 2002 and 2005. He was a research associate with the University of Virginia, USA during 2005 to 2006. And 2006, he joined in the University of Newcastle, Australia. You know that Dr. Zhiyong Chen is a renowned professor, and his research interests including nonlinear systems, control, biological systems, and multi-gen systems. Dr. Chen was and he is also serving as associate editor for the Automatica, IEEE transaction on automatic control, and IEEE transaction on cybernetics. And Dr. Chen has a lots of publication. He has more than 150 journals publication, more than 100 of conference, and several books and book chapter. Dear audience, we will listen valuable talk regarding secure network control of large-scale cyber physical systems using cryptographic technique. It's a very important, and we will listen at the most experienced person about the how we can secure our network for the LSS system, that is large-scale cyber physical system using cryptographic technique. So I want to request Professor Zhiyong Chen, please start your valuable speech, and dear audience, be patient. Hopefully, we'll enjoy this session and write down your question and your thoughts, and there will be a valuable discussion session, and we will have time. We'll enjoy. Please, Dr. Zhiyong Chen.
Yeah, thank you. Yeah, thank you very much for first of all the invitation to ask me to give this presentation here, and also thank you very much for the very nice introduction to myself. And yeah, it's my great pleasure to give a presentation here for this conference. Unfortunately, because of the COVID, and we cannot show, and we have to run this conference online. So uh, before I give the presentation, let me share my screen so that you can see my PowerPoints. Okay, so can you see that? Is that all good?
Yes, you can see. Yeah.
Okay, good. Thank you.
Okay.
Yeah. Yeah, the presentation today I'm going to give is about the secure network control of larger scale cyber physical systems and using cryptographic techniques. That is some joint work I recently did with my colleagues here at the University of Newcastle. And this presentation, actually this talk is very very technical actually, so I'm sorry if you don't have the background in this area. It probably will make the presentation a little bit harder to follow. I'm sorry for that. So I will try my best to not to touch too many technical details. I just to try to present the basic ideas as much as possible. So yeah, that's a joint work with two of my colleagues, and I acknowledge their contribution to all the works I presented. I'm going to present it today. In the presentation, first of all, I would like to give some basic introduction, and then of course, so I need some preliminary and some problem formulation, and then I will introduce the so-called double layer cryptographic architecture, and that will be used to solve two problems. And I list the two case studies here. One is for centralized stabilization problem, and the other one is for decentralized consensus problem. And then it will followed by some simulation results and some examples, and as well as some concluding remarks. All right, let's start with the introduction. First of all, the target of this presentation is so-called large-scale systems as well as network control systems. So basically, the large-scale system, I use the different definitions of large-scale systems, and the particular one I'm using here is the system that has multiple subsystems, has multiple entities. Okay, it's not just one single system. It's a system made of many different parts. It's more like a multi-agent system. So we've got many different agents and to make a system. And also we consider the scenario that the controller is designed in long distance. So that but basically we're talking about the network controllers. So that means, so I have an agent here, I have a different agent here, but the controller is not local. The controller is remote. Okay, every controller is remote. Now we have like these two scenarios are combined. So we will consider network large scale systems. That's the main target of this paper or this presentation. Sorry, I just turned off my phone. Yeah, And just two examples, like a group of Johns. So like this is a typical large scale and network control systems, because you can see we have a group of Johns, and the whole system, of course, is made of many entities. Okay, each entity is a John, and also in some scenarios, and the controller is not implemented in the John, and there probably will be a remote controller. So there probably will be a control station there. The control station will implement the controller in the control station, but not in these Johns. So that's why we have multi. So we have a larger scale system and with networked controllers. And this high-speed railway station is another typical example. And of course, the system is very large, and we get many networks. We get a large network, and with many trains running in this network, right? And all these trains, they work together as the whole system, as a whole network work system. And the controller actually, in most practical scenarios, the controller is implemented in a central station. So that's why that is a larger scale, a network control scenario. Okay, that's basically the scenario we are going to discuss today, and that's some graphic diagram of these two scenarios. This here, so this circle, this circle dots, they represent the different entities of a system, and here as well. And this one in figure one, so these different subsystems, they are coupled, they are physically coupled. Okay, and like the train, the railway system. So all the trains, they are kind of physically coupled because of the in the whole network system, and there are some kind of interaction. And this one is not coupled. Okay, and this one, and we consider these two different scenarios, different cases. The first case, and we consider the same. You can see this rectangle represents a controller. So that is just one single centralized controller. And we got a decentralized controller here. And each small rectangle block that represents a controller. And that, of course, that is the network. Okay, that cloud is the network. And now, so you can see some kind of keys and logs here. That's because we are going to talk about the secure control, secure performance of the controller. And we need to use encryption, decryption. I will give more explanation to see why we use two layers. You can see we have two layers of encryption here. So we got one lock and another lock on top of that. And then we got one key, and just kind of open this lock and then lock again, and another key and another key, right? And you can see they appear, of course, eventually they appear in pairs, okay, in pairs. But why do we need a two layers encryption? Oh, okay, that's the I'm going to give more explanation, of course. So, and what is the target? Okay, the target is, so we consider the situation where some dynamic entities or control units are vulnerable to disclosure attacks and can become malicious. So basically, because we are talking about the security, so security is with respect to different attacks. So what kind of attacks we are interested? So actually, we only interested in the so-called disclosure attacks. Basically, we don't want to disclose the information. Like for example, if I'm this circle, if I'm this subsystem, I don't want my state to be disclosed to anyone. I don't want this controller which run in a third. I don't want this controller to know my state. I don't want my neighbor or the other entities know my state. Okay, so I should keep my state, and when I say state, as also state, output, in kept secret to or to other agents or to other entities or to the controllers. Okay, so that's the basic scenario. So there are twofold security objectives here. So one is the input and output data of benign entity are protected from the malicious entities. The malicious entities can be the controller, can be the other entities. Okay. And the other one is the input-output data of the benign entities are protected when they are transferred over the networks in a distributed environment. When they are transferred here, of course, I don't want that be disclosed. And then you may say, okay, why? That's a very simple question, because you can put a log here, and then you can see the message can be sent out because it's locked, and it basically encrypted. When it's encrypted and nobody knows the private key, and nobody can know the information if I just simply transfer the information here to the controller. And then so the controller can design a controller based on this state. But the thing is, so if the controller has the key, to open this lock, then the information will be disclosed to the controller. That is not what we want, right? We want to keep the secret. We keep the state as a secret, not only to the environment, to other people. It should be kept as a secret to the controller as well. That's why the controller cannot see the message, cannot see the state. So that's the reason. So I use the two logs here. So the first log is two logs here, and basically the controller can open the second one, but it cannot open the first one. But how? So if it cannot open the first one, this gray one, if the controller cannot open that, then the controller cannot see the real information, right? The controller cannot see the real information, and then that's okay, that's good. But the thing is, how can the controller design a good control algorithm without the message, without the real message, just because the controller only sees the encrypted message? Okay, it can only see the encrypted message, cannot see the real message. And how to design a controller based on the encrypted message, based on the encrypted data? So that is a key thing, right? That is a key thing. So, and the good thing is there's some kind of algorithm, some kind of encrypted algorithms, and you can manipulate the encrypted version. You can manipulate the encrypted version and to get some kind of operation you want on the original data. And say that's the key. Okay, so I will give you a bit more details later, technical details later. But let me just finish the introduction, just summarize. So what are the technical challenges here? So the first one is about the controller design. So now we are going to design a controller in an encrypted state space. It's not like in a traditional controller design, and you have a sensor. A sensor can measure the state. And then you have the controller. Controller is designed based on the measured state. But now you don't have the state. You only have the encrypted state. Okay. What the controller can see is not the real like a 2-volt. If we are talking about the circuit, it's not like a 2.5 ampere or 2 or 5 volts. It's not like this kind of real data. What the controller can see is just kind of very arbitrary numbers. It's huge numbers because it's in an encrypted state space. So the first technical challenge is how to design a controller in an encrypted state space, right? And the second one is, so we also need to make sure that so the closed loop system gains and the states, they need to match the specified cryptographic algorithms. Because when we use cryptographic algorithms, and the algorithms must be applied on a given domain, like the range. Okay, you can only encrypt data between, for example, between 1 and 1,000, for example, and you can only encrypt the numbers in this region. That's why when you design the controller and your closed loop system, when the closed loop system runs, you must make sure all the gains, all the inputs and outputs of the system must always match these regions, must always in that particular region. Okay, that's the two technical challenges. And to address these two challenges, we of course proposed some algorithms, proposed some controllers, And the main contributions of these proposed algorithms and controllers are listed here. So the first contribution is we present a novel double-layer security scheme using cryptographic mechanisms. And the second one is we give a systematic technical methodology based on the principle of separation. So the principle of separation here means I do the encryption algorithms and the controller design separately. So all the encryption design can be used for different systems, for different scenarios. I give two different scenarios here. One is stabilization, one is consensus. But it can be applied to more different scenarios, okay? Because they are separate. Of course, the third contribution is this method is applied to the particular two control problems, as I just mentioned, stabilization and consensus. Okay. And then, so I use a motivating example to explain why it's needed, why a double layer strategy is needed, why we cannot just use one pair of key and lock. Okay. I use a very simple scenario, and we got agent X and agent Y. We call that as Alice and Bob. Okay, Alice and Bob, and they don't trust each other. They don't want to disclose the information, the state, to the other one. Okay, and the third one is called the controller. The controller is a third party controller, and they do not trust the controller either. Okay, they don't want the controller to see the state. And the state is X for Alice, and Y is the state for Bob. And because the controller need to manipulate these two states, they need to know, for example, now I want to do a controller which is X plus B, X plus Y. So the output is a very simple controller. I measure X, I measure Y, I add them together as the output. Okay, it's a very simple linear controller, just as an example. So, and now I use epsilon A as one kind of encryption algorithm. This epsilon means encryption, and this A means the key, the public key that is used to do the encryption. So if Alice and Bob, you use the same keys. If both of them use A and B other keys, if A and B they are same, okay? If A and B are same, then there's no secret between Alice and Bob, right? If because they know the key, they use the same key. So that basically means you cannot use you cannot use the same key for Bob and Alice because they want to keep secret from each other. So that's why this A and B should be different. However, so if A and B are different, and then when the controller receives epsilon AX and epsilon BY, and controller has nothing, don't have anything, cannot do anything. So we will see that if A and B are same, then the controller can do something to get X plus B, X plus Y. But if A and B are different, the controller cannot do that. So that's the reason we cannot just use one single layer of encryption. So one single layer encryption is not enough. So that's the reason we proposed a 2 layers encryption. And there's some technical details here. So how to do this, how to design this crypto system, how to do the encryption, how to do the decryption. I just ignore the details here. So, and the particular, because I'm talking about the 2 layers encryption, and the one is called RSA crypto system, and the other one is called Palea encryption crypto system. So these 2 are very famous, very popular in methods, okay, for encryption. And the Palea crypto system has an interesting property. We call that as a homomorphic property. Okay, that property is listed in this formula. So, so that means you can see. So if we have epsilon P and 1, here P is a key. the public key to encrypt the message M1, and also we do the encryption for message M2, and M1, M2. Now we want to get the sum of M1, M2, and we don't want to disclose decrypt them. So the good property here is, so if you just simply multiply epsilon PM1 and epsilon PM2, okay, because you don't need to describe that, you get these two encrypted messages, you multiply them, okay, you get the product, and the product is nothing but the M1, M2, the sum of M1, M2 in with the encryption. Okay, so if someone, if the controller can do this, say controller receive this message from the first entity, from Alice, and receive this second message from Bob, and then what the controller need to do is just to do the multiplication, and then send that back to the entity, and then the entity can, because it encrypt with the key P, and it has the private key to decrypt that, and then it will get M1 plus M2. So the controller can get the operation without knowing the real message. So that's the beauty of this Pioneer crypto system. We call that as additive homomorphic property. We're going to use this property to design controller. Okay. And before that, some preparation need to make. So the first preparation is we need to convert everything. We need to convert all the signals, analog signals, into integers, because all these encryption algorithms are used for integers. Okay, only in integer you can do that. That's why we need to have, when you have an analog signal, you should quantize. They should be quantized, and then the quantized signals will convert into integers. Okay, and also that's a very technical part. I use different notations in the paper. If you, by the way, so if you are interested in this work after the presentation, and you can read my paper, and they can get more technical details there. And I list some notations here. So yeah, sorry, if you don't mind, just give me 10 seconds. My phone is keep ringing. I just ask him to wait for a second. Okay, sorry. Someone probably is calling me urgently, so just give me 10 seconds. Okay, so sorry for that. And now, so let's come back to the system description. So that's a larger scale control system. So X is the state, and the U is the input, and Y is the output. And this F and H are some nonlinear nonlinear functions that just describes the general larger scale control systems. And here X is the state, as I said, Y, U is input, Y is output, and X is the lumped state of a whole system. I put, because I got N capital N entities and put them all together is the full state. Okay, we call that X. And then encryption, the whole controller design is not just simply design U based on Y or X. That was the traditional control, right? We design a controller U based on X, which is a state feedback, or based on Y, which is the output feedback. But now it's not like that. So we don't know the controller doesn't know X or Y, because those they want to keep it secret. And that's why the first step is to do encryption. So, and the about Y here is encryption of Y, and I put a Q here. This postscript Q means that's the quantized version of Q of Y. Okay, and also I need to encrypt both Y and the negative Y, because both Y and the negative Y will be used in the future. And And unfortunately, so this Pioneer crypto system, as I mentioned before, that is only for additive. That cannot be used for subtraction. That's why, so I cannot use M1 minus M2 here. So that's why I need to encrypt both y and negative y in case I want to do x minus y, a minus b. So that's why I can do a minus b as a plus negative b, right? So that's why I need to encrypt both y and the negative y. And then that's a controller, okay? That's a controller. And the controller doesn't know, you can see the controller, I did not use y here. I use a bold y, which bold y is the encrypted version. It's not the original y. So, and the controller now use bold y. Of course, the controller want to do some kind of decryption, but this decryption cannot cancel this epsilon. This D1 to Dn does not cancel E1 to En because for security reason. For security reason, so if D1 can cancel epsilon 1, that means V or the controller can see this Y directly. That is not allowed. So that's why I don't have that. And this Z, and this Z is the state of the controller. So Z basically is, if we are talking about the dynamic controller, we have this Z. You can understand that as observer. Say observer is a dynamic part of the controller, right? And Z is the state of the observer. And the Z0 comes from the some kind of design, okay? And then, so once you get this V, and then we want to transfer this V, which is a controller, back to the system. And before the transmission, and that V should be encrypted as well to a bold V. And then when you receive this bold V, and you can decrypt that and to get the U, okay? The agent can get U. And you can see that's the whole process. That's the whole process. And by doing that, by doing this process, and we can prove that, and all the signals, all this security can be maintained. So that security I mentioned before, okay? This twofold security objective can be achieved if we do this kind of process. In particular, of course, we need to, when we do that, we should select this epsilon here, this D here, and very carefully, very properly selection of this encryption decryption can make the target, okay? And now let's more formally define what signal. When I always say the signal is secure, it keeps the secret. And what does that mean? So the mean is, so a signal AK is secure in a ciphertext, which is the encrypted version of AK. I use bold AK to a party if the private decryption key is unavailable to the party. So if the key is unavailable to the party, that means that signal is secure to that party. And the system is secure if the following two properties are satisfied. The whole system is, that gives a definition of secure signal, and that gives you a definition of secure system. So if both the output and input are secure in the encrypted version Y and V, and to all entities and to all control units except the self entity. Of course, it cannot keep secret to itself, right? So if this is secure to all the other entities and to the control units, and then we say that is a part of a secure system. And also, the signals, they are also secure in this decrypted version, because the controller can decrypt the outer layer of the encryption. So that is with the outer layer decrypt, and that is still secure to the control units. Okay, still secure to the control units. And if both of them are satisfied, we say the system is secure. And now we can say the overall objective, the problem formulation can be given like this. So overall objective of the work is to find the encryption and decryption protocols, which are the epsilons and the Ds, and the private control algorithms represented by those functions, and which is the function used to design the controllers. If we can find that such that the system achieve because we consider two different scenarios: stabilization and the consensus. For stabilization, we want to all closed loop system is bounded by the initial condition with the low k, and the low is between 0 and 1. Low is between 0 and 1. That's why when k, which is time, goes to infinity, and all the states of the closed loop system will converge to 0. Okay, that's the stabilization target. Of course, there will be some kind of error, okay, because of the quantization. So we cannot get a perfect 0. Okay, there will be some error. And you can see with a large M, this error will be smaller. And M is a resolution of the quantization process. And the consensus problem. The consensus problem is not to drive X to 0, but to drive X to all the X. So all xk, which is the state of different entities, to the same value, and which is x infinity. Okay, with some x infinity, there exists some x infinity such that xk goes to x infinity and connect multiplied by 1. This 1 is a vector whose entries are always 1. You get 1, 1, 1, 1, 1, 1. So that is this bold 1. You can see. So and then this whole product will be s infinity, x infinity, x infinity. So all the entities are x infinity. That means all the xik will go to x infinity. That is called consensus. And this error will converge to 0, right? And of course with some kind of error, with some kind of error there. So that's the first performance. That's the control performance. And the system should be secure in the sense of definition 2, as we just described. And now, so we have the general secure network control design paradigms based on this separation principle. Okay, again, I'm not going to get into all these technical details. I just roughly say explain this main theory. So the main theory is, so if we can do the design such that these three properties are satisfied. The second one is the controller subject to perturbation. So that is a controller, the traditional control in the original in the plain state space. It's not in the encrypted state space. So basically, the idea here is, if you want to design a secure controller for the system to achieve some kind of performance, one condition is you should be able to design a controller for that without considering the encryption, right? So if you cannot design a controller for a system without considering the secure issue, how can you design a controller for the system by considering the secure issue, right? So that's why the first condition is, yes, there exists a controller without considering the security issue, and just using the original states, I can design a controller, okay? So that's the first condition. And we will talk about how to design this controller for the stabilization and the consensus problem in the case studies. And the second property is the quantization property. Of course, as I just mentioned, that we need to quantize the signal and then convert the signal into integers. So that is formulated here. And the second one is we should have some cryptographic property. And that I don't have time I don't want to get into the technical details why that is formulated or why we have this kind of formula. And then if these three properties can be satisfied, then we can say the system achieve P1, which is a stabilization or consensus. So, and the second theorem here tells us, okay, that gives a specific design of this algorithm and the functions and the controllers such that, okay, and this property, so this cryptographic property will be satisfied. Say, because in theorem 3.1 we say, okay, you should have property 1, 2, 3, then you get the P1. And the second theorem tells us, so I give you an explicit selection of this method, of this algorithm. And then one of the property can be automatically guaranteed, which is this cryptographic property, and then P2, the security property can be guaranteed as well. So if by combining these two theorems together, so we can say to solve the original problem, the only thing we need to do is to find a controller without conceding the security. Okay, so that is the reason we call that as a separation principle. And now, and be more specific, and I give to these two controllers. One is, okay, I have a multiple input, multiple output system, which is AIJ, AI, BI, and XI. And I want to design a controller like that. And now, so the tricky part here is I have to guarantee all these gains. This is a part of the controller. They must be integer. Okay, they must be integer. So that's why that puts some kind of challenge to the controller design. It's not like the traditional control, because we know for this system, linear system, to design a stabilization controller is super easy. So you can easily find that from any linear, modern control course. Okay, any modern control textbook. But here, so the more difficult part is, so we need to make sure all these controller, these gains, they must be integers, because without the integers, the controller in the encrypted version of the controller cannot be implemented. Okay, because the encryption can only be, the Pioneer algorithm can only be applied to integer numbers. Okay, and again, I don't want to touch the details. I just want to say the assumption here is A, B, C, A, they're controllable and observable, of course. So that's always the assumption we need. And then we give a lemma tells us how to guarantee there exist integer gains. Okay. And then here's the theorem. Here's the result. So we can, by using that kind of integer matrices designed by the previous lemma, and we can guarantee this performance. And that is the stabilization. You can see this low is between 0 and 1, and that goes to 0, and there's some kind of small error here. And also we can guarantee that all the state y and the input, the output y, the input u, and the state of the controller, they're always in this range, so that the encryption algorithm can be applied. So that is called to avoid the so-called overflow issue. So if the states go out of this range, then we call that is kind of overflow. Okay, and of course, so that is achieved only when the initial conditions have some there's some, the initial states must satisfy some initial conditions. So basically, we say this initial condition should be smaller enough, which is R0 given by this number. Okay, so if the initial condition is too large, unbounded, then there's no way to keep all the input output within this specified range, right? So that doesn't make sense. And then put all these things together, we solve the problem formulated before. And here is the example. I give some numerical example, and you can see, okay, that's the states of two systems, x1 and x2. They converge to some small value, and that's I zoom in here, and you can see there's some error. Of course, if I use a smaller m, use a large m, here m is 6 here. If I use m is 9, the error becomes smaller. If I use 90, of course, the error is kind of, becomes even more, even smaller, and you cannot ignore, you can think practically ignore them. And that is the state of the observer. And this state, you can see it does not, you cannot tell any real information from these states, because they are all like 10 to the 37. That's the encrypted version. Some kind of numbers, integer numbers. You cannot tell any real information from there. So that is the secret of the system. And similarly, we can do the similar thing for the decentralized consensus problem. And again, one difficulty here is to keep all the control gains as integers. and the other one is to keep, I ignore the details, sorry. So, and the other one is to keep all the states within this range, okay? All this should be, they bring the challenges to the controller design compared to the original design in a plain text, a plain data space. Okay, so that's the conclusion as well. And let's show you a network. That's a large network. We got 100 agents here, and we want to achieve consensus of these agents. And each agent has this kind of oscillation behavior. And we can see that these 100 agents, their states converge to each other. That's, you can see they converge to each other. Originally here, you got 100 different values here, but when time goes, and you can see they all converge to each other. And that is basically the consensus error that goes to a very small number, some kind of small, almost close to zero because of the quantization error there. And that's the input. That's the input you can observe. And you can see the input is some kind of random numbers up to 10 to the 37. So that's because they are encrypted. And if you do want to decrypt, then you will get this kind of signal. That's the real signal, but that is the encrypted version of that. But the controller or other people or third party or other agents can only see these. They cannot see that. They cannot see figure 12. They can only see figure 11. So that's why that keeps the whole signal secure. Okay, the last page. So some concluding remarks. So in this presentation or in this this work, and we have designed a secure network control approach for larger scale systems with network control. And based on a separation principle, the double layer cryptographic scheme using Pioneer and RSA crypto systems and their designs so that they can protect the information of a ground entity and control units from any malicious party. And also we got 2 case studies on secure stabilization of multi-input, multi-output systems, and also secure decentralized consensus of multi-agent systems. And of course, there's some future works. And the first one, of course, we need to investigate. We probably can investigate the different homomorphic crypto systems rather than Pioneer. And then that means, so we probably can do more complicated nonlinear control scenarios. Okay, here, because as I said, we only use the additive homomorphic property that only apply to linear controllers. So cannot be applied to nonlinear controllers. And also we can investigate different cryptographic operations for achieving greater efficiency. So because for Pioneer and RSA, actually it takes some time, okay? Takes some couple of milliseconds for every encryption, decryption. Okay, that's my presentation. So thank you very much. Any questions?
Thank you very much, Professor Zhiyong Chen. Dear audience, we listen the valuable speech from Professor Zhiyong Chen. So now is the question answer session. We already listened valuable speech about the centralized network control, and he also mentioned the decentralized network control scenario. And we also listened what are the challenges of his work and what is the contribution regarding this work. Audience, this is the research work. I think our young researcher, we can ask the question to our honorable speaker, because already he mentioned the novel double layer security scheme. Dear audience, you know that the security is a great issue. He also presented the all variable status space and all algorithm, a lot of work. So I think it's a great time for us. This conference will be available for his space. Please make a question, and it is a discussion session. Please raise your hand, please. Ask a question. Any question from the audience?
So hi, Prof. Zhiyong.
Yeah.
Sorry, I have one query. It should be page number 14, I guess. 14.
Here. Is this page? That's page 14.
No. There was one initial value selection, and in that case, I saw that one of them was positive and one of them was negative. For example, Xi0 or something like that, and it was in a vector.
This one positive, one negative? No?
Yeah. EI, this one. So YIQK and minus YIQK. So what I was thinking is there any specific reason to be one as a positive and one as a negative? Is it like semi-definite things or something like that?
Yeah, good question. So because when we encrypt, so the controller will work on the encrypted version of Y. Okay, will work on epsilon Y, and they will do some manipulation. Say like I have two states, I call that Y1 and Y2. Now they need to calculate Y1 plus Y2. So that's they can use this property. Say Y1 here, Y2 here, and then they do the multiplication. They will get epsilon Y1 plus Y2, but they cannot do Y1 minus Y2. Okay, you cannot say I use this one divided by that one to get minus my minus m2. You cannot do that. That's why. But sometimes in the controller design, we do need y1 minus y2, right? So some control gain can be negative values. So that's why if I got y1 here, negative y2 here, if I encrypt both negative and positive, and then I multiply y1 and negative y2, and here what becomes y1 minus y2. So that's how I get y1 minus y2. That's why I need to encrypt both y and the negative y. Does that make sense?
Yeah, I understand. Yeah, thank you for the clarification.
Okay, thank you.
Any question or suggestion from the audience, please?
Yeah, I think probably this presentation is very technical, and maybe people will have more questions if they read the after read the paper. If interested. Yeah.
That's fine, Jansen.
Yeah.
Please, could you please say some word, Dr. Human Fad Rahman? Are you here? Co-chair of this session. Dr. Human Fad Rahman, are you here?
Dr. Fuad, we can't hear you.
Sorry.
Yeah, we can hear you now. Yeah.
There's some audio issues. Can you hear me?
Okay, yeah, we hear you. Please say something about this session, please. Dr. Fuad.
Prof. Zhiyong, sorry, I also have another query. Well, so this scheme can be applied to smart grid security, right?
Yes.
Yeah, I mean, so this is a two-layer things. So how does it offer when we consider it as a generalization? I mean, multi-layer?
It's not. So the reason I use two layers, so as I explained, because we got basically three parties. So you one remote controller and other agents. But there's no at this moment. I don't see a point to do more layers. So 2 layers is useful, but to do more layers, it kind of redundant. It's not necessary. And regarding the application in smart grid, and we do have a paper published recently in IEEE transaction on smart grid that is about using this kind of algorithm, encryption algorithm, to keep the privacy and the security of a smart grid. So if you are interested, you can have a look at that paper.
Yeah, okay, sure.
Okay, good. Thank you.
Thank you.
Now we can now conclude. I think there is no question from the audience. There's the last chance. Do you have any question? I think no question, because it's a research presentation. So audience, you know that controller design is a great challenges, and with this encrypted state space is also a great challenge. Already Dr. Zhiyong Chen mentioned these challenges, and he has some great contribution about this research. So let's thank to Professor Dr. Zhiyong Chen for his nice presentation.
Yeah, thank you very much. Thank you for thank you all for your attention.
Yeah, thank you.
Good, thank you. Bye bye.
Audience, we can switch on our video, and then we can take a group photo with our speaker.
Take a photo.
Yeah.
Yeah, I will take a photo as well.
Okay. Thank you very much for a nice day. Have a nice day. Yeah. Thank you. Nice day with this conference with the today and tomorrow. And be safe. Don't worry. In this pandemic situation, I think it's a great job, and especially thanks to Department of Mechatronics Engineering, right? Because with this pandemic situation, this type of organizing, this type of conference, brainstorming, obviously it is a good idea. So again, thanks to the organizer and the technical committee as well. Okay, I see you.
Hi, Sir Hafiz will give the session keynote speaker certificate, I guess. Hafiz, would you like to continue?
At this stage, our session chair, Professor Dr. Mohammad Selim Hossain, will hand over a certificate as a token of appreciation to our honorable keynote speaker, Professor Dr. Zhiyong Chen.
Professor Zhiyong Chen.
I guess Professor Zhiyong Chen has left the session.
Okay. This is a token of appreciation to Professor Zhiyong Chen for his valuable speech for the secure network control of a large-scale cyber physical system using cryptographic techniques. It's a research work that basically is a more valuable for this controller design. Again, I can say controller design is a very challenging work. So again, thanks to Professor Zhiyong Chen for his nice presentation. Okay.
Ladies and gentlemen, it's time to appreciate our honorable session chair and co-chair. I, on behalf of the organizing committee, I feel honored to share the session chair and co-chair certificate to our respected session chair and co-chair as a token of appreciation. Now I will open the certificate for session chair and would digitally like to request our session chair to receive it.
Okay, thank you very much.
Thank you, honorable session chair. Now I would like to request our session co-chair to receive the certificate as a token of appreciation. Thank you, honorable session co-chair. Thanks all of you to present in this glorious session, and thanks you all for your participation in this session and make the session live. With the permission of the session chair and co-chair, I would like to close. I like to close the session. Thank you again.
Yes, please.
Thank you, sir.